Final thing, the last thing in all of your physics education, the last thing that I'm covering is the Doppler effect. The Doppler effect is an apparent shift in frequency produced as the source of a sound or light moves. It can be moving away from the observer, it can be moving closer to the observer. In both cases, it produces the Doppler effect. If the object is moving closer, it appears as if the waves are being squeezed closer together and the wavelengths are being shortened. As the object moves away, it appears to the observer as the waves are being stretched out, or their wavelengths are getting longer. So this is the wave that the car, horn, siren, whatever the case might be, is producing. And this is the wavelength of that wave illustrated on the board. And if I measure the wavelength of this wave in centimeters, the car, horn, the siren is producing a wave that has a wavelength of about 7 centimeters. That's the normal sound. That's what the person in the car will always hear. Here the car is moving. And as you can see, in front of the car, the waves seem as if they are being squeezed together. And that causes an apparent shift in the wavelength. So over here in front of the car, it appears as if you have roughly a 2.5 centimeter wavelength. Again, remember, what the car is producing is a wave with a 7 centimeter wavelength. That is the actual sound. That's what the driver hears. That's what you would hear if you were riding with them. But in front of the car, it appears as if the wavelength has been shifted or shortened to 2.5 centimeters, because as the car moves, it appears to be squeezing the waves. Behind the car, it appears as if the waves are being stretched out. So if we measure this wavelength down here, it's 8.5 centimeters. It appears as if the wavelength has increased to the observer on the outside watching that car go by. This will affect the sound that that horn or that siren produces. Because remember, wavelength and frequencies are related. Whenever you shorten a wavelength, you will increase the frequency. So as the object, the car in the case of my picture, moves closer, the sound that the horn or the sound that the sirens make will sound like it's a higher frequency than what it really is. And again, that's because the waves have been shortened, and shortening the wavelengths would increase your frequency. As the object moves away, again, the wavelengths are stretched, they appear to be longer wavelengths, we would hear that as a decrease in frequency. So if you've ever heard a car go by, it kind of, with the horn blaring, it kind of goes, ear, as it goes by. High frequency when it approaches, low frequency when it moves away. That's the Doppler effect. Again, for sound, it's observed as a change in pitch. As it moves closer and the frequency increases, you hear it as a higher pitched sound. As the object moves away, the frequency decreases, so the sound becomes lower pitched. You hear it in the engine noises of race cars on NASCAR races as they're flying by the camera. High pitch as they approach, low pitch as they move away. In reality, the pitch is always the same. The driver's not changing the RPMs of the engine, it's staying constant. You listen to the in-car cameras, it sounds pretty steady the whole time. But to the camera on the outside, again, high pitch as it moves closer, low pitch as it moves away. That's, again, the Doppler effect. It does happen with light as well. For light, frequency is perceived as color. You know the spectrum: red, orange, yellow, green, blue, indigo, and violet. Red is the lowest frequency of those lights, and violet is the highest frequency. When we start shifting the frequency of light, we start changing its color. So as a light source moves closer, its frequency is again increased, so it moves us towards the higher end of that spectrum, towards blue and violet light. That's called a blue shift. As the source of the light moves away, again the wavelengths are stretched, the frequency drops, and the light shifts towards the lower frequency end, or the red end. We call that a red shift. You've probably heard about the Big Bang Theory and the idea that the universe is expanding. This is one of the big pieces of evidence that plays into that. When we look at every other galaxy in the universe, the light it's producing is shifted towards the red end of the spectrum. And that red shift tells us that those galaxies are moving away from us. This is also the same principle that's used in Doppler radar. When they start talking about Doppler radar showing a potential tornado, what they're doing is they're shooting radio waves at the storm clouds. And those radio waves are being bounced back towards the receiver. Now, if that radio wave hits rain that's moving towards it, it'll squeeze the radio waves and the receiver will get a higher frequency radio wave back. If the rain hits the waves hit rain that's moving away, that's going to stretch the wavelengths and the receiver is going to get a lower frequency wave back. And then by calculating how much it's shifted, they can figure out how fast the raindrops are moving and be able to see when it's moving closer, when it's moving further away. And when they see a radar image that shows rain over here going this way, rain over here going that way, there could be a circulation in between. Keyword is could be, because it can't tell what's going side to side. It can't tell if it's going up, over, back, over. It can't get the side parts. So they say there's a possible tornado in that area. It's also a radar guns work. Again, shooting radio waves at cars. When the car is moving towards you, it will squeeze the radio waves that reflect back, and the radar gun will receive back a higher pitch radio wave. They use how much it's been shifted to calculate how fast you're going. It's all Doppler effect. And that's it. That's physics. It's a wrap. Sayonara.